Hello students, in this video let us discuss some problems based on the hydrogenation reaction which are very useful for JEE advanced exam. Okay, so let us start without any delay. So here generally hydrogenation is the addition of the H2 to the alkenes or alkynes. In this reaction we will get the alkanes, and the addition of the H2 is the exothermic reaction. That means delta H is the negative, and this is the adsorption based process. So first here H2 addition on the metal catalyst, and then here that the metal which is absorbed by the H2 is added. That means here that is approaches to the alkene, will get the alkane. That means here that H2 can be removed from the metal surface, that is added to the alkene or alkane, so we'll get the finally alkane. So here the mostly one important point is addition of the hydrogen is a syn addition, because here these two hydrogens are added to the alkene from the same phase. Okay, so that's why it is a syn addition reaction. That important point is syn addition reaction. Okay, so hydrogenation is a syn addition reaction. So let us discuss some example based on the stereochemistry of this one. Okay, so here first of all, the based on the stereochemistry, uh, so here in this case, for suppose this one is the double bond, here CH3 and CH3. So this one on reaction with H2 in the presence of the nickel. Okay, so generally we are saying this is the H2 addition, that is the hydrogenation is a syn addition. So syn addition means here these two hydrogens are maybe above the plane or maybe below the plane. That means here this is the methyl below the plane, this methyl below the plane. So here that can be approached from either side. Okay, so generally here for suppose this one, this is the planar molecule. Okay, this is the planar one. So about this double bond, hydrogen is approached from the top face or below face. So here in this case these hydrogens are above the plane. That means here this the metal which is absorbed by the hydrogen approached from the top face. So of course here that also approaches from the below the plane. So here we can get the hydrogens below the plane. So now here ultimately the methyl groups above the plane. Okay, so it is a syn addition reaction. That means here those two hydrogens either both above the plane or below the plane. Okay, so what is the relation between these two actually? So actually here there is a plane of symmetry, here also plane of symmetry. That means here this is a meso compound, this is also meso compound. These two meso compounds are identical or homomers. So finally we will get this single compound. Okay, in this reaction. For suppose, so let us discuss this one, CH3 and CH3. This one is the methyl, that is the above the plane, of course. Okay, that means here additionally one stereogenic center is there. So now here in this case, this product is optically inactive, and this reactant is optically inactive, and the product is also optically inactive. Okay, so here in this case there is no chiral carbon, but here in this case there is a chiral carbon. Even though it has a chiral carbon, it is optically inactive. Why? Because this one has a plane of symmetry. Okay, because here in this case methyl below the plane, methyl below the plane, here methyl above the plane, methyl above the plane. So this one has a plane of symmetry, so optically inactive compound, even though it has a chiral carbons. Okay, so a optically active compound, even though it has a chiral carbons, that is known as a meso compound. Okay, now in this case initially this compound is optically active because of this chiral carbon. Now here this one an addition with H2 in the presence of the nickel. So here in this case this one above the plane. Now here this one methyl above the plane. Now this is the methyl above the plane. It means here hydrogen is approaches from the below the plane. Okay, that's it. Now here that hydrogen may be approaches from the above the plane. That means here methyl here above, that fixed one, that is here in this case methyl below the plane, hydrogen above the plane. Here also hydrogen above the plane, here methyl below the plane. So that means in this case here both products are possible maybe. So here in this case what is the relation between these two? Here in this one these two are the non-mirror images. Okay, because here the configuration at this chiral carbon is not changed, that is fixed. Okay, these two are the non-mirror images, so the relation between these two diastereomers. Why? Because in this case This compound is optically inactive compound. So here you can see the carefully this compound I am writing like this here. This one is the above the plane, this one is the above the plane, this one is the above the plane. All methyl groups above the plane in this case. So this compound has a plane of symmetry, so optically inactive compound. Okay, but in this case here, this one is the above the plane, this one is the below the plane, and this one is the below the plane. So for this molecule here, plane of symmetry is not possible. Okay, so this compound is optically active compound and this compound is optically inactive compound. But here what is the relation between these two compounds is the diastereomeric relationship. Okay, that's it. So here one more example we will discuss. For suppose this is a simple alkene. Here these are the hydrogen, this is the hydrogen. For suppose this one addition with the D2 in the presence of nickel or platinum, any metal catalyst. So here in this case, the maybe here deuterium above the plane, here also deuterium above the plane. So or maybe here deuterium below the plane, here also below the plane. That means here this one has the plane of symmetry, this one has the plane of symmetry. Again here, as in the first case, these are the meso compounds. Okay, that means we'll get the single compound. So these two meso compounds are identical. Okay, so next here, for suppose this is a cyclohexene. Here in this case alkyl group methyl, here alkyl group is ethyl. As earlier as we discussed, this is the methyl and this is the methyl and this is the methyl. Both are same groups. Okay, so then here plane of symmetry can be possible. So, but in this case here, one is the methyl, one is the ethyl. In this case, the plane of symmetry is not possible. So here, this one on reaction with the H2 in the presence of nickel. So H2 addition is a syn addition. So those two hydrogens are added from the above the plane or below the plane. Okay, those two hydrogens above the plane now. Here in this case, methyl below the plane. Here in this one, ethyl below the plane. Next year, another isomer also possible. So that is the hydrogen here below the plane, this hydrogen below the plane. Now above the plane ethyl and this above the plane methyl. So now here what is the relation between these two? These two are exactly mirror images. Okay, it is a chiral carbon, it's a chiral carbon, it's a chiral carbon, it's a chiral carbon. Okay, of course here this compound has two chiral carbons. So and here these two are the mirror images. The relationship between these two are the enantiomers. Okay, so why these are enantiomers? Why these are optical active? Because there is no plane of symmetry. Here methyl and ethyl, the different alkyl groups, say symmetry is not possible. But here in this case, the symmetry is possible. Here methyl, same group, so there is a plane of symmetry, so optically inactive compound. So here only single compound, that two optically inactive. But in this case here, the two compounds are possible and each one is the optically active compound because there is no symmetry. One is the methyl, one is the ethyl. Okay, so that is also one of the beautiful example. Now for suppose, so here in this case one more example. So this is the methyl. For suppose above the plane, this is the alkene, this is the CH3. Now this one reacts with the H2 in the presence of the palladium. So here in this case, this is the methyl, the fixed one that is above the plane. And next one, here in this case hydrogen added. Already there is a hydrogen, now here another hydrogen is added, so it's not a chiral carbon, so you can ignore the stereochemistry at this carbon. Okay, so now here methyl is there. So if the hydrogens are added from the above the side, so here above the plane hydrogen, below the plane methyl, and here the another isomer possible is this one, so CH3 and this hydrogen below the plane or above the plane methyl. Okay, so that means in this case, this is the hydrogen above the plane, of course here hydrogen also above the plane, here hydrogen below the plane, of course here hydrogen, one hydrogen above the below the plane. So of course, but in this case here at this carbon two hydrogens are there, so stereochemistry is not playing important role at this carbon. Okay, so but here if you consider these two carbons, in this case methyl above the plane, methyl below the plane, so it is a trans 1,3 trans compound. Here methyl above the plane, here methyl above the plane, that is the 1,3 cis compound. So what is the relation between these two? The diastereomers. Okay, because the cis and trans are non-mirror images and diastereomers. And in this case, cis compound is optical. Sorry, the cis compound is optically inactive compound, and this trans compound. Sorry, yes, this trans compound is optically active compound. Here there is no plane of symmetry. So methyl above the plane, methyl below the plane. Here methyl above the plane, here methyl above the plane. There is a symmetry possibility. So it is optically inactive compound. okay, and one is optically active compound. But here relation is the diastereomeric relationship, okay, and that means in this case the above the here there is a chiral carbon, there is a chiral carbon. That means here inactive compound, so it is known as a meso compound, okay. The compound, even though it has a chiral carbon optically inactive, simply we are saying there is a meso compound, okay, but it is not a meso compound, optically active compound. And what is the relation between these two are the diastereomers, okay. So next here, the one more example, let us discuss. For suppose in this case, this is the methyl above the plane, this methyl above the plane, okay. So this is the alkene. This one reaction with the D2 in the presence of nickel. So let us write the products of this reaction. Above the plane methyl, above the plane methyl, okay. So now here this one deuterium above the plane, here deuterium above the plane. Now another possibility, above the plane methyl fixed. Now here that may be deuterium approaches from the below the plane DD, okay, so both below the plane. So then what is the relation between these two? So these two are the non-mirror images, okay. So but there is a plane of symmetry. Actually this compound can be cut into two equal halves, and those two equal halves are the mirror images each other. Now here these two are the also that means two equal halves, those two equal halves must be mirror images each other. So this is the optically inactive compound, this is the optically inactive compound. So this is the inactive compound, and this one also inactive compound, but not identical, okay, but not identical. Why? Because here in this case this chiral carbon configuration is fixed in both cases, but at this chiral carbon configuration is different, okay. So that's why these are not identical in this case, okay. Of course here both are meso compound, this is a meso compound and this is also meso compound, but not identical compounds these are. So here next, so let us discuss one more example, that is, for suppose here this is the methyl above the plane, here this is the double bond CH2. Now in this case H2 in the presence of the platinum oxide, this platinum oxide is known as the Adams catalyst, okay. So now here the syn addition means, so methyl above the plane, here in this case methyl above the plane, okay. So why? Because so here in this case the hydrogen is added to one carbon, here hydrogen added one carbon, okay. So for suppose these two hydrogens are added to the alkene from the above this side, so that means here so one product is like this. So this methyl is fixed, so these two, the H2 molecule is added from the above the plane, so then here hydrogen above the plane, so then here CH2 on addition becomes a CH3, that means here below the plane methyl. Now in the, another case, if a hydrogen is added from the below the plane, that means here a hydrogen below the plane, then here the CH2 and a hydrogen is converted to CH3, and that goes to the above the plane. That means it is a cis-isomer, it is a trans-isomer. So then what is the relation between these two diastereomers, okay. And in this case here again the cis compound is optically inactive compound, so because of the plane of symmetry. So and this is also known as a meso compound, okay, and trans compound is optically active compound, okay. So that is the stereochemistry of the hydrogenation reaction for cyclic compounds, okay. So now here coming to the acyclic compounds. So generally here let us discuss for the acyclic compounds. Now here this is the cis-alkene, okay. So you can see this is the cis-alkene, this cis-alkene on addition will get the meso compound, okay. So in this case some conversions are required, so here based on the stereochemistry. So first here this is a cis compound, it is a hydrogen is added, that means here the hydrogen is added to the alkene from the one phase, it is a syn addition, that means here the hydrogen below the downward direction, here hydrogen downward direction, okay. So now here for our simplification we can convert this compound, okay. So here by converting this compound like this, here methyl downward, here methyl downward, so deuterium goes to this side and a hydrogen goes to this one, okay, this place. So next here like this we can see here the deuterium goes to this place and methyl comes to downward direction and the hydrogen goes to this upward direction. So now here from this structure we can write the 2D representation. So here whatever the groups which are in downward direction must be on the vertical line in a Fisher projection formula. Okay, so I'm repeating again. So what are the groups which are on the downward direction must be on the vertical line. So here methyl, methyl, so methyl, methyl, and at this carbon, that means it is, this is the top carbon, so this is the top carbon. So okay, it is downward carbon, so this is the downward carbon. So at this carbon, deuterium on the right left side, so deuterium left side, hydrogen on the right side, here hydrogen on the right side, deuterium on the left side, so that's it. So we can simply write the, you can convert the Newman projection or Sauer's projection to the Fisher projection formula. Okay, so here that means here in this case the cis compound on addition with the hydrogen, that means here cis compound on syn addition will get the meso compound. Okay, so see this one. Now this is the trans compound, this trans compound on addition with the hydrogen, so we will get this one. So hydrogen downward direction, here hydrogen downward direction. So again here for our simplification we can convert this structure. Okay, let's convert the structure like this here, 120 degrees angle. So here deuterium goes to this place and the methyl goes to that means in the downward direction, this hydrogen goes to this place. Okay, so you can see this one. So now here this one again rotating 120 degrees. Okay, that means here methyl comes to downward direction and the hydrogen goes to this direction and deuterium comes to this right side. So now here what are the groups which are on the downward direction must be on the vertical line in a Fisher projection formula. So now here at this carbon, so deuterium on the right side, so right side. So hydrogen on the right side, here hydrogen right side. So what are the groups which are on the right side? We can write the right side in Fisher projection, and what are the groups which are present on the left side? So we can write on the left side in a 2D representation. It's nothing but Fisher projection. So in this case we'll get the optically active compound. Okay, this optically active compound. So actually of course here every alkene has two phases. So because that compound is a planar compound, so either front side hydrogen can be approached or from the back side hydrogen can be approached. So that means that there are the two possibles for the reaction of H2 with the alkene. So for suppose this is the one possible. So hydrogen is added from the one phase. So here another possibility we can see here, the hydrogen is added from another phase. So we will get the another isomer. Okay, we can repeat the same process. You can see this conversion also. So then finally we'll get the compound that is also optically active compound. And here in this case these two compounds are different. Why? Because these two are the mirror images each other and the enantiomers each other. Okay, so here in this case the point is the trans compound and syn addition will get the two compounds, that is a racemic mixture. Okay, so why? Because the racemic mixture here in this case here the compound alkene is a flat. Okay, this alkene is a flat compound, so exactly that has a gives a equal chance for the addition of the H2. That means here 50% is can be added from the one phase and other 50% can be added from the another phase. That means here there are the two possibilities, equal chances. So we'll get the 50% of this isomer and 50% of this isomer. Okay, these two are the mirror images and enantiomers. So enantiomers in 50-50%, that is nothing but 100% racemic mixture is produced in this reaction. Okay, so actually here this is for the symmetrical alkene. Okay, so I am saying again this is for the symmetrical alkene. So actually here in this reaction, okay, so here in this case hydrogen is approached from the one phase. Of course hydrogen can be approached from the other phase also. Okay, so if hydrogen approaches from other phase we will get this compound methyl and methyl, but here this is the optically inactive compound due to plane of symmetry. So that our optical activity is cancelled. That means this compound can be it can be cut into two equal halves. The one equal half optical rotation is cancelled by the other equal half. That means it is a meso compound. It is a meso compound. These two meso compounds are identical each other. Okay, so that's why here we are saying only one compound, simply there is a meso compound. Of course here in this case, okay, so actually here it is symmetrical alkene. It is also symmetrical alkene. For symmetrical alkene, cis compound and synertion gives a meso. It is a trans compound and synertion gives a racemic mixture. Okay, these are two equal possibilities. Okay, here are also two possibilities, but in this case both are optically inactive, both are meso compounds identical. So that's why we are saying only one compound is a meso compound. But in this case for trans compound on hydrogenation, we'll get the racemic mixture. Okay, So now let us write for the unsymmetrical compound ethyl, this one methyl. So here a hydrogen, here hydrogen. Now this one on reacts with D2 in the presence of the nickel. So it is an unsymmetrical alkene. Why? Because in this case methyl and this case ethyl. So now here first of I am writing directly methyl and ethyl. Okay, that means here deuterium and deuterium, hydrogen and hydrogen. So actually here in this case we can see that when the compound is cis compound, so what are the groups actually that placed on the vertical line, and the groups which are added comes on the same side. Okay, so based on this point I am writing the products. So here deuterium hydrogen and deuterium hydrogen, this is a methyl and this is a ethyl. So generally here in this case there is no symmetry, each compound is optically active. That means here racemic mixture is produced. Okay, for cis compound also racemic mixture is produced when the given alkene is unsymmetrical. Okay, this is the unsymmetrical alkene. Okay, that's it. Now for suppose ethyl double bond, here methyl, the hydrogen and the hydrogen plus D2, the presence of nickel. So now here I'm writing again products methyl ethyl. So actually here you can see here for trans compound here the whatever the groups which are added, so comes on the opposite side, hydrogen and hydrogen, here hydrogen and hydrogen. That means here I am writing the products based on this, that one. So here what are the groups, deuterium and here deuterium, so remaining hydrogen and hydrogen. Now here this methyl ethyl deuterium hydrogen, so hydrogen and deuterium. So what is the relation between these two? Again enantiomers each other, that means here these two compounds are formed in a equal chances. So here 50% of this compound and 50% of this compound, so racemic mixture. That means it is optically active mixture, it is also optically active mixture. But here in this case when unsymmetrical alkene is taken in a hydrogenation process, we will get the erythroisomers. That means erythro enantiomers we will get. Okay, the similar groups on the same side, so that generally we are calling erythroisomers, and here similar groups on the opposite side, so generally we are calling those are the threoisomers. Threos isomer, that means threo enantiomers. Similar groups on the opposite side, so threo enantiomers, here erythro enantiomers. Okay, when the alkene is an unsymmetrical alkene. So that is the stereochemistry of the hydrogenation of acyclic compounds. Okay, so here the one question you can see, that is from the JE Advanced 2015, the compounds that are on hydrogenation produce optically inactive compound. So for suppose this one on addition with the H2, so Br, and this is the hydrogen. So this alkene converted to alkane. So here still all this is the optically active compound. Methyl and propyl hydrogen Br optically active even on hydrogenation. Here in this case this one converted to propane. So this one also optically active compound. Okay, because the different groups are there. So initial optical active compound, here initial optical active, after hydrogenation optical active, here also after hydrogenation optically active. Now coming to this one. So here in this case, this one are addition with the hydrogen converted to ethyl. Now here above the plane bromine and below the plane hydrogen. Now on both sides similar groups, so optically inactive compound. Initial optically active compound, but after hydrogenation, after H2 addition, so that ethynyl group converted to ethyl. So on other side ethyl, so it is optically inactive compound. Okay, so now here also same. This is the ethynyl, this is the ethyl. On hydrogenation, that is converted to ethyl groups. So these two are the correct options. That means here the product is optically inactive compound. Okay, so that is about the hydrogenation. That means the stereochemistry of the hydrogenation reactions. Okay, so thank you for watching. Please subscribe my channel for more videos.